So this is definitely a concept that goes above and beyond this course, but it helps explain an equation that we're going to look at here. And although water is a covalent substance, a very small amount of it will react with each other to transfer protons. So water mixing in and of itself can behave as an acid or a base. It's referred to as self-ionization, and very small amounts of H3O plus and OH minus are produced from this. So in this case, water is acting as an acid and the other water molecule is behaving as a base. And we get an H3O plus and OH minus from this. Now, I want you to keep in mind that every time water does this, we get one H3O plus and one OH minus from this. So the amount of H3O plus and OH minus will always remain equal to each other, right? You're not going to have one above the other because every time water does this, it produces one of each of these things. And a very small amount of H3O plus and OH minus are produced from this process. In fact, it's 1 times 10 to the negative 7th for each. So it's a very, 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 very small amount of H3O plus and OH minus that are produced from this. But because very little of this becomes product, we're in an equilibrium expression. And because we're in an equilibrium situation, we can write that expression for it. So if I go back, water and water are liquids, and we never include liquids in equilibrium expressions. So that means that Kw equals H3O plus times OH minus. And using the values from the previous slide, we can determine that Kw is 1 times 10 to the negative 14th, right? If I take 1 times 10 to the negative 7th for H3O plus and 1 times 10 to the negative 7th for OH minus, I multiply them together and get 1 times 10 to the negative 14th. What's nice about this is that this equation not only reacts or works for water, but it can be used to calculate the concentration for any ions present in these solutions. We simply plug in one for the other, and we can solve algebraically for these. Now, that negative 14 number might look awfully familiar to you if you are familiar with the pH scale. You might know that the pH scale runs from 0 to 14. And that's actually where the 14 comes from, is this auto-ionization constant of water. So based off of this formula, we can do some calculations and determine how much H3O plus and how much OH minus we get from this. And then we'll evaluate what that information means a little bit later on. But for right now, what I'd like you to do is I'd like you to go through and try to do some calculations with this. We'll walk you through it step by step here in just a moment. But remember, we have that formula, Kw equals H3O plus times OH minus. Remember that Kw is 1 times 10 to the negative 14th, so just plug some numbers in and algebraically solve for the unknown concentration that's listed here. We'll bring it back in just a moment. All right, so we're going to go ahead and solve for this. I got up my handy-dandy little calculator to help us out, but let's go through and see what we can do to calculate these out. Now, let's remember our equation here. So we have Kw equals 1 times 10 to the negative 14th, and Kw equals H3O plus, stylus is not behaving today, times OH minus. So this simply becomes a plug and chug algebra problem. So we're going to take 1 times 10 to the negative 14th. That is equal to, I'm given an H3O plus, which is 4.0 times 10 to the negative third. And we multiply that by OH minus. And then again, we just do a little bit of algebra here. So what we're going to do is we're going to take 1 times 10 to the negative 14th, and we're going to divide that by 4 times 10 to the negative third. If you need to, put it in parentheses, like I forgot to do. And so what we get here is our OH minus equals 2.5 times 10 to the negative 12th. Okay. These are concentrations, so we are going to use M to describe them. Or the OH in brackets also describes concentration as well. We're going to apply the same exact concepts to the problem down here below. So we're going to take 1 times 10 to the negative 14th. We need to find H3O plus, that is our unknown. And we're going to plug in our OH minus. So 1.2 times 10 to the negative 9th. And we're just going to algebraically solve for that like we just did. So 1 times 10 to the negative 14th divided by 1.2 times 10 to the negative 9th. Again, parentheses, please. And what we get is 8.3 times 10 to the negative 6. sorry, my calculator was not in scientific notation, so I actually had to think about it. And that is equal to my H3O plus. Okay. Now, these numbers don't mean a whole lot to you at this point in time. That's what the next slide is going to show you. It's going to tell us that the relative amounts of these materials is going to tell us whether the solution is going to be acidic or basic. I will bring you back in just a moment and show you how to go through and do that. So why do we go through and calculate H3O plus and OH minus? Well, it's a way for us to be able to determine that if it's... So what's the reason why we go through and calculate H3O plus and OH minus? Well, that information helps us determine if a solution is going to be acidic or neutral. An acidic solution will have an H3O plus concentration that is higher than that of OH minus. And a basic solution is going to have an OH minus that is higher than that of H3O plus, and a neutral solution will contain the same of each. So the graphs here are a little bit confusing, all right? But the further you go down, the more concentrated it is. It's a little bit difficult to interpret here, but the very first solution you have is a neutral solution where we have equal amounts of H3O plus and OH minus, just like what we discussed before. Those will be 1 times 10 to the negative 7th for each of them. As we add H3O plus, we actually eliminate OH minus. So as the H3O plus concentration increases, OH goes down. H3O plus is in greater concentration than OH minus, so the solution is acidic. And the opposite's true. If we end up with more OH minus, that means that H3O plus decreases. We have more OH minus, so it is a base. So go back and take a look at the previous couple of problems and think to yourself, is this base solution acidic? Is this solution basic? Is it neutral? Remember, compare the relative amounts of them, and remember that your exponents are negative. So keep that in mind as you go through and evaluate those. And this might be a little bit better way to examine the relationship here. You look at the chart down at the bottom, a little bit easier to interpret here. A neutral solution is where H3O plus and OH minus are equivalent to each other. An acidic solution is where H3O plus is greater than OH minus, and basic is where OH minus is greater than H3O plus. So again, just another way to visualize the information that we've just taken a look at and that we've just covered. Now, as non-scientists, or as many of us are non-scientists just out in the real world, it's inconvenient to work with those numbers. You don't go to somebody at the pool store and go, oh, well, your H3O plus concentration is 1 times 10 to the negative 5th. You need to add a little bit of base to it. First off, you're going to get punched in the face. And second, you're probably going to get called a nerd. For some people, that's a compliment, like me. But anyways, we simplify this information by using what's called the pH scale, which is a much easier way, it's a much more simplistic way to determine if something's acidic or basic. Basically, to determine the pH, you need to take the negative log of H3O plus. And so this actually makes this scaling a little bit different. With the pH scale, it's a log-based scale. And logs are what are called base 10, which means that the difference of a pH of 1 is actually a difference in 10 times the acidity. So for example, something that has a pH of 2 compared to something that has a pH of 3, well, the one that's 2 is 10 times more acidic than the one with the pH of 3. We'll examine the pH scale in just a moment to determine if something's acidic, basic, or neutral. But for now, I'd like you to go through and calculate the pH of the following solutions, giving the H3O plus concentration. So just simply take the negative log of these values, and you will get the pH. And then we'll take a look in just a couple moments to determine if they are acidic or basic. Be back with you here in just a couple moments. All right, so here we're given a couple of different concentrations of H3O plus, and we're trying to determine the pH of these solutions. So we'll do a little bit of help with this. If the pH is less than 7, it is an acid. If the pH is greater than 7, it is a base. And if the pH is 7, we'll call it neutral, okay? Just to kind of give us an idea. So we're just gonna plug these into our calculator and solve. So this is actually very easy to do. So negative log, and then I'm going to type 6.3 times 10 to the negative 5th, and I get 4.20, or 4.2 if we use proper sig figs. This would be an acidic solution because it is less than 7. So do the same thing again. In fact, what I'm going to do is I'm just going to change the number. No, I'm not. I'm going to just type it in again because that's actually easier. So take the negative log of 5.3 times 10 to the negative 5th. We get 4.3, still an acid. And then here, 2.2, oops, negative log. Follow your own directions, Joe. Seriously. You're trying to help people here. 4.7. So all these are acids, okay? But again, the numbers there are much easier to interpret than, say, the exponents that are available, all right? Let's move on. So now we want to do the inverse function with this. This isn't something that I've gone through and discussed right away, but what you'll notice is that a lot of times on your calculator, the inverse function is just the secondary function of the button that I've pressed. So I'm looking at my calculator right now, and the log button, the secondary function of that is 10 to the power of. So if I want to go the reverse direction and solve for H3O plus, you're going to take 10 and raise it to the negative pH. It's a pretty simple way to go through and solve for some of this, but again, we're just looking at going the reverse direction here. So if I want to do this first one here, I'm just going to calculate the H3O plus. (10 to the negative 1.2). And I'm going to do that for all three of them. So take a moment, go through, calculate those. We'll be back in just a moment and calculate the rest of these. So go ahead and calculate the first one, which is going to be 6.3 times 10 to the negative second. Remember that these are concentrations, so molarity of H3O plus. So off to a good start. Let's do that with negative 6.9. So what we end up with here is 1.3 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. I think it's negative 7th. Then lastly, we do it for negative 10.4. Much easier there. You get 4.0 times 10 to the negative 11th. So again, just a couple of easy ways to go through and do some calculations with these pH numbers. Just make sure you have the ability and flexibility to work back and forth between the different formulas that we've looked at. We've looked at three, right? Kw equals H3O plus times OH minus. The negative log of H3O plus equals pH. And then 10 to the negative pH will equal your H3O plus, right? Let's move on and keep working. So as I mentioned previously, and we'll keep taking a look at this moving forward, an acidic solution, it has a pH that is less than 7. A basic solution has a pH that is greater than 7, and a neutral solution has a pH that's equal to that of 7. So much, much easier to determine if something's acidic, basic, or neutral based off of the pH scale. And again, keep in mind that each number on the pH scale is base 10, meaning that, let's say we look at something with a pH of 1. Something with a pH of 1 is 10 times more acidic than something with a pH of 2. Something with a pH of 1 is 100 times more acidic than something with a pH of 3. They're multiplicative as you work through them. So again, just a couple of things to think about. Oh my goodness, it's like I just mentioned this. I forgot this was a slide that was coming up, but reiterate the point that I last made. It is a log-based scale. So a solution that has a pH of 1 is 10 times more acidic than with a pH of 2. A solution that has a pH of 1 is 100 times more acidic with a pH of 3, and so on. So multiplied by 10, and they're multiplicative. So something to just kind of keep in mind. Here are some common liquids and various pHs that are on some living tissue here. So battery acid, acid cleaning products have a pH of less than 1. They're very acidic, can be very damaging to living tissue. Gastric juice has a pH of 1 or 2, can be very irritating. Citrus juices and vinegar, those have a pH range of 2 to 5. They can be irritating to mucous membranes. Don't be snorting citric juice. 5 to 8 is usually pretty non-hazardous. Cola drinks, coffee, tap water, intestinal fluids, urine, etc. You start going up the scale, you get more basic. These can be a little more harsh. Seawater, soap, you get soap in your eyes, it's pretty painful. Household ammonia and bleach, and then oven cleaner, drain cleaner, very, very hazardous. So most people just have this notion that acids are the only ones that are dangerous, and that's not true. In fact, bases can be quite as dangerous, if not more dangerous than acids sometimes, because most people don't think of bases as being toxic or dangerous to human health, but in fact, they quite are. And here's a table that just shows some normal pH range of select body fluids. I want you to notice very closely blood plasma, very, very strict range of pH, because you can have some very, very serious medical issues, things like ketoacidosis and whatnot, if you have a blood pH that is outside of that range. So just some things to keep in mind. Now, when dealing with a specific chemical, we need to know first off whether it's an acid or base. So I'm not always just going to give you, hey, this is the concentration of H3O plus, hey, this is the concentration of OH minus, go through and calculate it. What I am going to tell you is this is a concentration of an acid, this is a concentration of a base. Now, when we do this, we're only going to be dealing with strong acids and bases, so it makes it a little bit easier. So for example, if I give you a chemical that is an acid, that's the same as the concentration of the H3O plus, and then you do your negative log accordingly. If it's the concentration of a base, it's the concentration of OH minus, you'll have to do a little work to get the H3O plus and then calculate the negative log from there. Again, think about the variety of different equations that you have as you go through and work through some of these problems.